On the actual Unit 7 test, you're going to have this chart here. So remember that that's going to be a useful chart. Okay, let's look at number 1. Okay, number 1 says a galvanic cell was constructed by placing tin in a solution of tin chloride and zinc in a solution of zinc chloride. Okay, that's kind of a standard thing. So we're looking at this sort of a cell. Which of the following takes place at the anode? So built into this, there's some thinking you have to do. So you say, well, I've got tin and I've got zinc. So I've taken those two and I found them on my chart and I wrote them down. And I found out that the tin has a voltage of negative 0.14, zinc negative 0.76. So my zinc, my tin is the more is a larger number. It's a smaller negative number, larger number. So that's going to be my cathode. That's going to be reduction. And therefore my zinc is going to be my anode. But when I use it, I'm going to have to reverse the reaction. So instead of tin being oxidized like we would see it, tin being reduced like we see it here, you have to turn it around. So the actual equation is going to be zinc turning into zinc ions. Up here in the reduction potential, it's zinc ions turning into zinc. It's going to be the other way around. So it's answer B. Okay, number 2. Okay, what is the value of E cell for a galvanic cell that undergoes this reaction? So we have to look at the reaction and say, okay, what do they have going on? Okay, their aluminum is changing to aluminum ions, aluminum to aluminum ions. We say, well, that is oxidation. Okay, that's the reverse of what's happening in the chart. So this E of the this change, okay, is going to be the E oxidation, and it's going to be positive 1.66 volts. So in the chart's negative, this is going to be positive. I'll write it again, positive 1.66 volts. Okay, the copper is a reduction. As you see, it's 2 plus changing into copper neutral, and on there that is positive 0.34 volts. So we're going to add those two together. So 1.66, 0.34, and that is going to come out to be 2. So the answer here is B. Okay, for the third, we say, okay, we've got a cell, a galvanic cell again. It's constructed by placing an unknown metal X in the solution of X2 plus and lead in the solution of Pb2 plus. And the E of the cell is found to be positive 2.24. So we're going back to our equation, okay, and this is the useful equation, and we know that the cell is positive 2.24 volts. So now we have to figure out the other two. One of them is lead, okay, so we know that lead, way back here, is negative 0.13 volts, okay, so we're going to use that. But the question is the lead being reduced or is the lead being oxidized? So we're going to put in negative 0.13 volts here. We're going to put in positive 0.13 volts there. And that's the key. So here's the other clue. After some time, the mass of X decreases while the mass of lead increases. So that means X, if it's decreasing, it must have started as a metal and it's turning into ions. Okay, so that is oxidation. So that means that the X is this chemical and the lead is this chemical. So we're going to use lead as is. So we're using negative 0.13 volts here. And now we're looking for, I'm going to say X, for the oxidation potential. So what happens here is I'm going to say, well, it's 2.24 equals negative 0.13 plus X. So that means X is going to have to be larger than 2.24 by 1.13, just add 0.13 to both sides, and I get 2.37. So the oxidation here of X must be positive 2.37, but we're asking for what's the reduction potential, so we have to change the sign, so we're really going to say it's negative 2.37. So again, because of the logic that says, that the X is losing mass, okay, then we know that that's the oxidation. So when we plug it in here and we get positive 2.37, that's the oxidation potential. We have to reverse it for the reduction potential. The other clue is that the lead is gaining mass, Okay, and that makes sense because now we're saying lead ions pick up some electrons and becomes lead metal. Okay, so that would cause it to gain mass. Okay, question 4. We have zinc and we have lead, and they're placed in a solution of nickel. So we have nickel, we have zinc, we have lead. So I look back at the chart, and I wrote these three in order. Okay, I don't really care about their number, they just care about the order from the reduction potential chart. And I'm talking about nickel ions, so I kind of put a box here around nickel ions. So I say I can have nickel ions and I can put it with lead metal, or I can have nickel ions, I can put it with zinc metal. Which of those is going to lead to a reaction? Okay, and I know that this is going to go forward if this goes in reverse, okay, because I have my greater reduction potential going forward and my lesser reduction potential going backwards. So nickel ions would react with zinc. They would not react with lead metal. So nickel ion, zinc metal. So the answer is B, zinc only. When we get to number 5, what is the delta G for the following reaction? Okay, well, we know that this equation, delta G equals negative NFE, and that is on the periodic, that's on the back of our periodic table, but it will be on the AP exam as well. So if we can find the voltage of this reaction, then we can just substitute it in and figure out delta G. So what do we know? We know that Mn2 plus is changing in Mn. Okay, Mn2 plus changing in Mn. And if I go back and look at my chart, I see that that is negative 1.18 volts. Okay, and that is a reduction, so I'm going to use that number as is. Now here's Fe2 plus changing into Fe3 plus. Well, if I look back at my chart, okay, what it says is there's Fe3 plus changing, Fe3 plus changing into Fe2 plus, and that's positive 0.77. So here, the other way around, it's going to be negative 0.77. So I have negative 1.18, and I have negative 1.77. So my E of my cell is negative 1.95. So now let's go back to our equation. So negative N. Okay, if I put this together, there's 2 electrons, and I'm going to double this, and there's going to be 2 electrons. So 2 electrons, 2 electrons. So N equals 2. So negative 2. F is 96,485 joules coulombs per mole. And the E we just figured out there is negative 1.95 volts, which is joules per coulomb. Okay, so I have 2 times 96,485 times negative 1.95. I know you can't read that. And that's going to be 376,000, and that's coming out in joules, okay, per mole. And what we have is we have kilojoules, okay, and so I need C, which is 376 kilojoules. So I have to do this problem. I have to figure out my voltage, plug it into this equation, and then calculate. It's a little messy, sorry. Okay, number 6, we have a silver and copper galvanic cell, and they're placed in solution with 0.5 molar silver and 0.5 molar copper. What can be concluded? Okay, well, first off, we have to do some background, and we say, well, if I have silver, that's silver ions plus an electron becomes silver, and that has a higher potential than copper 2 plus, okay, because that's copper 2 plus. So copper 2 plus 2 electrons becomes copper. So this second reaction is going to be flipped around. That's going to be my anode. And to put these together, I'm going to double this first equation. So when I do it, I'm going to have 2 silvers and a copper, okay, turn into 2 silver metals and copper ions. Okay, so here's my overall reaction. And I need that because if I'm talking about changing my concentrations, I need to calculate Q. So Q is going to be the concentration of copper ions divided by the concentration of silver ions squared. So here's my expression. Then what I'm going to do is I'm going to put in, if I had a standard solution, it'd be 1 over 1 squared, which is 1. Standard Q is always 1. But now it's 0.5 over 0.5 squared, which you can see 0.5, 0.5, that's going to cancel. So what this really is 1 over 0.5, which is 2. Okay, my Q turns into 2. If Q is larger, then it's closer to the KEQ, which is some large value, which means my voltage is going to be smaller. Since my Q is larger than standard Q, 2 is larger than 1, then I am going to have a slightly smaller voltage. So the cell potential is less than the standard cell. This is my answer. Answer A. Okay, go to number 7. Okay, number 7 says a solution of unknown pH is placed in a hydrogen compartment of a galvanic cell. Now that we've talked about it, so you just have to know what that is. And I tried to draw a little simple picture. So you'd make a cell, and what you'd have is a beaker with 1 molar hydrochloric or 1 molar hydrogen ions, and we'd have a little platinum electrode, neutral, with hydrogen gas bubbling over it. So when that happens, you get this reaction. Some hydrogen ions pick up electrons and become hydrogen gas. Hydrogen ions get reduced by picking up electrons, become hydrogen. And that is just defined as 0 voltage. This is not even on our chart. You're just supposed to know this. So hydrogen ions plus electrons. Okay. The other one is copper, and we've seen that a couple times. So copper picks up electrons, becomes copper. That's positive 0.34 volts. So the reaction is my copper ions will react with my hydrogen gas. Copper ions and hydrogen gas turn into hydrogen ions and copper metal. So I can write a Q, okay, and I get hydrogen gas squared, hydrogen ions squared over copper ions and hydrogen gas. Now, this, we can see if I have 0.34 and 0, then my voltage for my standard cell is going to be 0.34. Okay, but I have a voltage of 0.65. So what can I do to my reaction to cause it to be a higher voltage? And specifically, we're talking about the hydrogen ion concentration, okay, because those are our choices. So hydrogen ion concentration. So you can see that there are really 2 questions here. One is, what is the role of the hydrogen? Is it the anode or the cathode? And since we see it has the smaller value, then we know that this reaction gets written in reverse, and it's the anode. So hydrogen is the anode, so we can knock off these 2 answers. Now what's happening to the hydrogen? Okay, the ion concentration. Well, if my voltage is larger than my standard voltage, that means my Q must be farther from my KEQ. In other words, I need a small q. I need my Q to be smaller than standard. Okay, smaller than standard. Here's my hydrogen ion concentration. If I want Q to be small, I need a smaller numerator, and a smaller numerator means less than 1 molar. So my answer here must be C. The hydrogen is the anode, and the hydrogen ion concentration must be less than 1 molar. Okay, number 8. What is produced at the cathode when 1 molar NaCl is electrolyzed? Well, this looks like a really simple little question, but it actually is lots of thinking, okay, that you hopefully have gone through a lot so you can do it quickly. So if I have a solution of sodium chloride, that means I'm going to have sodium ions, I got chloride ions, and I have water. Okay, I have a positive electrode and I have a negative electrode. Okay, well, negative electrode, that is going to be where electrons are pumped into this piece of metal. It's going to cause whoever touches it to gain electrons, and that's the key. So we're going to gain electrons, and we know that when you gain electrons, that's reduction, and if that's reduction, this is the cathode. So this is the side we care about. So we don't care about what's going on the positive side, where chloride will give off electrons and water will give off electrons. So, chlorine forming, oxygen forming, that was true. That's going to form, the things are possible, but they're going to happen at the anode. So it's not chlorine and it's not oxygen. Okay, over here at the cathode, okay, possibly we're making sodium metal, or remember that water can be reduced and we will get hydrogen gas. And if we look at the numbers, we say, okay, the chance of making water, it's negative 0.83 volts, and this is, negative 2 point something volts. Okay, so the water is the one that is going to be reduced. So hydrogen is the chemical that's actually going to occur, and it's answer B. Okay, so it looks like a simple problem, but you have to go through this thinking, okay, with a cell and figure out who's the cathode, what's going to happen at the cathode, and of these two choices, which one really does happen, and it's hydrogen gas is going to form. Okay, number 9 and 10, these are calculations. So the first off, we say, how long will it take to plate 0.1 grams of copper from a copper nitrate solution if the current is 8 amps? Well, okay, current is 8 amps. We're going to turn that into the idea that there's 8 coulombs per second. That's what amps mean, is that we're going to have a circuit where 8 coulombs of charge go through the circuit every second. So 8 coulombs per second, we'll need that. It also implies, because of this copper nitrate, that is the copper 2, it's going to pick up 2 electrons to become copper metal. So for every 2 moles of electrons, we get 1 mole of metal. Those are 2 things we need. So now we just set it up. Okay, we have 0.1 moles of copper, 0.1 grams of copper, copper 0.1 cam. And then we're going to go grams to moles, so this is just the molar mass. And then we use this equation here, our balanced equation. So for every 1 mole of copper, it takes 2 moles of electrons, so that's our balanced equation. Then moles of electrons to coulombs, that is Coulomb's law, Faraday constant, sorry. And then from our little idea of the definition of amps, we get 8 coulombs per second, and then we just do all of our mass, so grams of copper, moles of electrons, coulombs, and I got 37.956 seconds. So that's going to be 38 seconds, answer C. So that's how we set it up. Again, molar mass, this is implied by the fact it's copper nitrate, and this is given us because of the fact it's 8 amps. Okay, number 10, similar. Okay, not exactly, but it's a similar problem. How many grams of sodium will be deposited from a molten NaCl by a current of 3 amps? Now it's molten NaCl, melted NaCl, very hot. Okay, but that really makes no difference. Okay, we're talking about sodium forming, so we don't have to worry about the water. But just for molten there, we're going to make sodium, we're going to make chlorine. But we're talking about sodium. Current of 3 amps means that there's 3 coulombs per second. We can use that idea. And since it's NaCl, we know that 1 plus an electron turns into sodium. So 1 mole of electrons will give us 1 mole of sodiums. We're going to use that idea. So we start off and we say, okay, 4 hours. So 4 hours. And we know that for every hour there's 60 minutes, and for every minute there's 60 seconds. Okay. And then we can use our amp idea that every 1 second we get 3 coulombs. We got our Faraday constant that there's 96,485 coulombs in a mole of electrons. From our equation up here, we know that 1 mole of electrons will get us 1 mole of sodium. And then we need the molar mass of sodium, that there's 22.99 grams of sodium for every mole of sodium. Multiply this all together, we get 10.29 grams. Okay, and from our choices, rounded off to 2 significant figures, that's 10 grams. And that's answer B. That's the multiple choice. Okay, for the free response. Okay, this is from 2014. This is relatively recent. And what happens is a student is given a standard galvanic cell represented above that has a copper electrode and a tin electrode. Now, you cannot go back and look at that chart that we gave on the first part of the test because that was not part of this. That you can't use that as a clue. The clue comes from, it says the student determines that the copper electrode increases in mass and the tin electrode decreases in mass. That's the clue. Well, if copper is increasing in mass, that means copper ions, okay, are picking up electrons and becoming copper metal. So this guy is getting bigger and bigger and bigger. And the tin, okay, if it's decreasing in mass, that means tin metal, okay, must be turning into tin ions and losing electrons. So this guy is going to get smaller and smaller because we're going to get ions going into solution. So identify the electrode at which oxidation is occurring. Okay, well this guy is losing electrons. Okay, that's oxidation. So it's the tin electrode. Okay, explain your reasoning. Okay, and then we can just say, well, because we know that the tin is losing electrons, it must be, it's losing mass, it must be tin turning into tin ions. Okay, and that's losing electrons, and that's oxidation. as the mass of the tin electrode decreases, where does the mass go? Well, the mass, that used to be part of this electrode, is now going into solution as tin ions. Okay, so it's losing mass into the solution as tin ions. Is going to go away. Now, there, across the nation, people were a little confused, and they were saying, well, electrons are leaving, okay, and going this way. And that's true, okay, they are leaving, but the electrons have tiny, tiny, tiny mass. So they really, that is not the reason why the tin is losing mass. It's losing mass because it's forming ions in solution. Okay, so where does the mass go into solution? As tin ions. Okay, expanded view of the center portion of the salt bridge is shown. Okay, so we're saying, well, here's our salt bridge. We're going to look at that kind of close up. And it's got KNO3. Okay, in the expanded view of the center portion of the salt bridge shown, draw and label the particle view of what occurs in the salt bridge as the cell begins to operate. Omit solvent particles and use arrows to show the movement of particles. So what do we have? Initially, okay, and notice it says as it begins to operate. Okay, so initially all we have in here are K plus ions and we have NO3 minus ions. Okay, and what's going to happen to those is that the positive ions, okay, we decide this is oxidation, so this is the anode. And this is reduction, so this is the cathode. And one thing we learned is that the anions go toward the anode and the cations go to the cathode. So the negatives are going to go to the right. And the positives are going to go to the left. Okay, so if you wrote that, then you actually got the full credit. Okay, but here's the idea, is that on this side, okay, we are causing more and more positive ions to occur. So this solution, in order to keep it electrically neutral, we need some negative ions to work this way, okay, to help keep things neutral. In the same way, on the left side, some of our positive ions are becoming neutralized, so we need more positive ions to come this way, okay, to cause this, to stay electrically neutral. So the idea is that the positives are going to move to the left, the negatives are going to move to the right. Now you might say, well, I want to get those tin ions and stuff and everything in there too, but it says initially when it just begins to operate, so all we have are potassiums and nitrates. When we get to letter 6, number 6 here, D, okay, the non-standard cells made by replacing the 1 molar solutions with 0.5 molar solutions. The volumes of the solutions in the non-standard cell are identical to those in the standard cell. So all we're doing is changing concentrations. Is the cell potential of the non-standard cell greater than, less than, or equal to the cell potential? Okay, so if we're talking about cell potentials of non-standard, what we really want to look at is Q. Okay, that's what we want to look at. So let's look at the reaction. Okay, we've got copper turning into copper metal. We've got tin turning into tin ions. So the actual reaction would be copper ions and tin metal turns into tin ions and copper metal. Okay, I'm going to write that back down here. So we have copper ions plus tin metal turns into tin ions and copper metal. So Q is going to be the concentration of tin over the concentration of copper. And for standard cells, 1 molar is going to be 1. Well, what would happen if I put in 0.5 molar and 0.5 molar? Okay, nobody squared or anything, so that also comes out to be 1. So because my Q stays 1, then my cell potential is going to be exactly the same. Okay, I am the same distance away from my equilibrium, as I would be if I had a standard cell. So, since it's the same Q, okay, I'm going to get the same voltage. Okay? So same volt, I shouldn't say E0. Same E at E equals E0. Okay. Last little part. Both the standard and non-standard cells can be used to power an electronic device. Would the non-standard cell power the device for the same time, a longer time, or a shorter time? Okay, my new non-standard cell, I only have half as much chemical. I have 0.5 molar solutions instead of 1 molar solutions. Okay, so if I only have half as much chemical, it's only going to work for like half the time. Okay, I get the same voltage, but it's not going to work for us. It's going to, it's going to be a shorter time because my chemicals are going to run out. Okay, I'll say will be used up more quickly. So it's kind of a practical idea. We get the same voltage, but it's just not going to last as long. Okay, E, in another experiment, a student places a new tin electrode in a fresh solution of copper. Okay, so I've got a solution here with copper 2+ ions. I'm going to put a piece of tin metal in there. Okay, using the information in the table, write a net ionic equation for the reaction between tin and copper that would be thermodynamically favorable. Justify that the reaction is thermodynamically favorable. Okay, well, what am I talking about? I'm talking about copper 2+, so not this one. So this is good. And I'm talking about tin metal turning into tin ions. So that's ion, ion. I want this one. So these are my two that I'm going to be using. And I'm going to say, okay, my copper ions and my tin metal, okay, they will occur. So my reaction is going to be copper ions plus tin metal turns into copper metal and tin ions. Okay, and that's nice and balanced. So that's part of it. Now, why would I know that just the reaction would be favorable? Well, I could do my E0 value, my cell value, and that would be a good way to do it. And so what have I got? I've got positive 0.34 for my reduction potential. And because I had to switch this around backwards, okay, then I can change that to positive 0.14. So I'm going to get a positive voltage, okay, which is 0.48 volts. Okay, positive voltage is a thermodynamically favorable cell. So I can do that. I can just say, well, since it's positive voltage, it's going to be thermodynamically favorable, and that'd be great. I could also discuss the fact that this is more likely to go forward and this will go backward. Okay, calculate the value of delta G for the reaction, include units. Okay, so delta G equals negative N F E0. Okay, so from our reaction, okay, you can see that I had 2 electrons and 2 electrons, so N equals 2 moles of electrons for every mole of reaction. Okay, Faraday is 96,485 coulombs for every mole of electrons. And the E0 is what I just figured out, positive 0.48 volts, which is joules per coulomb. Okay, so coulombs drop out, moles of electrons drop out, so I'm going to get joules per mole of electrons, and the value will be, okay, so I'd have negative, for a negative, and if I multiply those numbers together, I get 92,600. So the value is negative 92,600 joules per mole of electrons. I could also write that as kilojoules, negative 92.6 kilojoules. The fact that it's a negative, delta G means thermodynamically favorable, positive voltage, thermodynamically favorable, so that all makes sense. And that is the practice test.